Okay guys, in this video we are going to be starting focus number 6, which covers chemical equilibrium, and we're going to discuss the thermodynamic equilibrium constant for chemical reactions. So recall that our criterion for spontaneity, at least under conditions of constant temperature and pressure, is that the change in the Gibbs energy must be negative. And so for isobaric chemical reactions, which is the most common case you'll find in a chemistry lab, is that a chemical reaction will proceed spontaneously until the Gibbs energy reaches a minimum value. Okay, so basically what I'm saying is the Gibbs energy, it's a state function, it's a property of the system. For a constant pressure reaction, that function tends to a minimum in order to reach equilibrium. And the way that we are going to characterize the progress of the reaction on its way to equilibrium is using what's called the extent of reaction variable. And we're using this funny Greek letter, but it's actually something that you've seen before. And I just want to point out here, using the camera, that there's nothing magical about this extent of reaction. So let's just suppose that we have some stoichiometric reaction here. It really doesn't matter what the products are. And I'm going to set up an ice table, which you would have learned about in general chemistry. And so let's suppose that we've got, some number of moles initially of species A and some number of moles initially of species B, and you can do the same thing for the products. And then on the way for this reaction to reach equilibrium, the amount of reactants typically will decrease, and so we would write that as a minus, this funny symbol here for the extent of reaction. And for species B, because of the stoichiometric coefficients, we would write minus 2 times that value. And for the products, I don't know, let's go ahead and make it C plus 2D. We would have, let's assume that we have none of that originally. And then, we're going to be making, because of the stoichiometry, we'll be making that many moles of that product C, and then we'll be making twice that for product D. And then at equilibrium, we would have what we started with minus this extent of variable. For component B, it would be what we started with minus the amount that reacts. And for the products, it's going to be 0 plus this variable. And so you'll recognize this process from problem-solving techniques that you learned about in general chemistry and quantitative analysis. And so there's nothing fancy about it now. We're just using a different symbol in Atkins, and we're calling it the extent of reaction. You'll notice here this general formula that I have, the at equilibrium, or at any point really in the reaction, the number of moles of component J that you have is equal to the number of moles that you start with. So I could correct this notation a little bit. It's the number of moles you start with plus the signed stoichiometric coefficient here, which is minus 1 for component A and minus 2 for component B, times the extent of reaction. So this generic formula here fits each of these. The range of this variable, that is the numerical range, it really depends upon the number of moles of each species that you have present in the system. Okay? And so its maximum and minimum values will be determined by the limiting reactants in both the forward and backward direction for that reaction. On this slide, what we're doing is formally introducing the Gibbs energy of reaction. Now we've looked at that previously. In fact, what we've looked at previously is the standard Gibbs energy of reaction in some detail, and we've learned how to calculate it. What I'm introducing here is actually slightly different than what we've looked at so far. It's not unrelated, but it's actually slightly different. And so here's the formal definition of the Gibbs energy of reaction. It's formally a partial derivative of the Gibbs energy for the system with respect to the extent of reaction at constant temperature and pressure. So I guess stepping back a second, you can think of temperature and pressure as variables, of course, but for a chemical reaction, because the identity of the reactants and products are changing, you can also think of this extent of reaction as now a thermodynamic variable. And depending upon how far you are in the reaction progress, that's going to affect the value of delta G. And so here is the the continuation of the formal definition. So if you consider that the Gibbs energy is a combination of reactants and products weighted by their stoichiometric coefficients, it's a sum over the reactants and products. This partial derivative leads to this expression here, where the change in Gibbs energy is the sum over the chemical potentials of all of the reactants and products weighted by their stoichiometric coefficients. For each of these components in the reaction mixture, the chemical potential of that component is referenced against some standard chemical potential plus a correction factor involving the activities, which we looked at in the last video of Chapter 5. The criterion, the spontaneity criterion, still applies here. When this quantity is negative, that means that the forward direction of the chemical reaction is spontaneous. If it's positive, the reverse reaction is the spontaneous direction. And when delta G bottoms out, that is when this derivative is 0, indicating that you have a minimum, that indicates that the reaction is at equilibrium. Okay, so this goes back to this statement here. Chemical reactions have a tendency to occur until the Gibbs energy reaches the minimum value. Here's a graphic. So imagine that. So this x-axis here, this represents our extent of reaction variable. And over on this side of the graph, we have our pure reactants. And over on this side of the graph, we have our pure products. And what we're plotting along the y-axis is the Gibbs energy of that reaction mixture. And so this Gibbs energy right here when we're at pure reactants, it's the sum of the Gibbs energies of all of the reactants. Over here on this portion of the graph, the value of the Gibbs energy function would be the sum of all of the Gibbs energies of each product. And so what happens as we go from reactants to products? Well, we're converting some of our reactants into products. And so the Gibbs energy, since the two the different components don't have the same Gibbs energy in general, we see that the Gibbs energy changes as a function of the extent of reaction. So at first, where only a small amount of reaction has occurred, we see that the Gibbs energy is decreasing. Notice that the slope in this curve, right, this is Gibbs energy as a function of the extent of the reaction. So that's this derivative here. We are calling that derivative delta G. So at first, when we're very close to the reactants, we see that the slope is negative. Right? The slope of the Gibbs energy curve is negative. That indicates that the forward direction is spontaneous. If you went all the way over to the products, you'll see that the Gibbs energy curve turns over, okay? And then in this region, we see that the Gibbs energy, the slope, the Gibbs energy of reaction is positive in this region of the graph. And that indicates that the reverse direction is spontaneous. Now, where does the reaction reach equilibrium? It reaches equilibrium when the Gibbs energy has been minimized, right? And at that point, in the extent of reaction, that's where the Gibbs energy curve has zero slope. And so delta G equals 0 is our equilibrium criterion. And so you can imagine if you just combined some reactants that, okay, as the reactants start reacting to form the products, you're just going to be moving along this coordinate. If you overshoot, well, the thermodynamics is going to tell you that you have to go back the other way until you reach equilibrium. You can almost think of a ball kind of rolling around in this valley here. Eventually, it's going to come to rest at the bottom, and it'll reach equilibrium. Here in this illustration, it's really just kind of discussing it in terms of a slightly more concrete example. If you had a chemical reaction whose reaction Gibbs energy is negative 200 kilojoules per mole, that tells you that the forward direction is spontaneous. And for those conditions, you could produce 200 kilojoules of non-PV work, so electrical work, for example. However, if you were to consider the reverse reaction, that would have a positive delta G. So the delta G would be 200 kilojoules per mole in the reverse direction. And that would imply that you need to put in at least 200 kilojoules of work to get that spontaneous reaction to occur. And so this highlights the minimum-maximum definition of delta G in terms of, or I should say, interpretation of delta G. In the spontaneous direction, delta G represents the maximum amount of work that you can get. However, in the reverse direction, delta G represents the minimum amount of work that you would have to do in order to get that reaction to occur. And that's highlighted here in this figure to some extent. So suppose that if you look here on the right, okay, so imagine that the process of lifting this mass up, independent of what's on the other side of the divider here, that's a non-spontaneous process, right? The mass spontaneously raising itself off the ground is non-spontaneous. Well, you can get that non-spontaneous process to occur provided you carry out another spontaneous process that has a larger value magnitude of delta G. So you can cause this non-spontaneous process to occur, but you need to use another process that has an even larger magnitude of delta G to make it occur. So that's illustrating the interpretation of a positive delta G as being a minimum amount of work. Well, let's keep going. So what I'm doing here is expressing the change in Gibbs energy relative to its standard in terms of this correction factor here, this RT natural log of Q, where the definition of the delta G standard is just this combination of chemical potentials and signed stoichiometric coefficients for standard state conditions. And then what's left behind is this correction factor involving the activities. And just to show you where this is coming from, what I'm doing is I'm taking this definition of delta G, which you have here, and then I'm substituting in this expression for each of those. Okay? So when you substitute for this chemical potential, when you substitute this expression in, you're going to wind up with the sum of the standard chemical potentials. And then you're going to have a second sum involving a sum over the natural logs. And if you use the rules of natural logs, you can write that sum of natural logs as the natural log of products and quotients. And that's what's done here. Okay, so this term here, this is the first term you get. That's the delta G that we've learned how to calculate previously, the standard Gibbs energy of reaction, which we typically calculated in terms of Gibbs energies of formation using Hess's law. The correction factor here involves this reaction quotient, which is a product over the activities of all of the components of the reaction mixture raised to the stoichiometric, the sign stoichiometric coefficient of that particular reactant or product. And so just to give you you already know how to do this. This is that products over reactants type of approach when you learned about equilibrium constants. So how would I write the equilibrium or the reaction quotient for this particular reaction here? I'd say Q is going to be equal to products, so the concentration of C raised to the stoichiometric coefficient, concentration of species D raised to its stoichiometric coefficient of 2. The sign stoichiometric coefficients of the reactants are negative, which is going to put them in the denominator. So we're going to get A to the 1 power, B to the 2 power in the denominator. Here I've done this in terms of concentrations. If I were to use this formula, I probably should have used the formula on the slide. So let me try that again. It's a product, like so. And so I'll just write this. I'll just go from left to right now. So component 1 is species A. So I'm going to write the activity of species A raised to its signed stoichiometric coefficient, which is -1. Then the next factor will be the factor for species B, raised to its signed stoichiometric coefficient of -2. The next factor, activity of species C, raised to its signed stoichiometric coefficient, which is +1. And then finally the last product, D, raised to its signed stoichiometric coefficient. And so that gives us the activity of component C times the activity of component D squared over the activity of component A times the activity of component B squared. Here I've used different units. I've used molarity as the unit of concentration. Here we're using activities. So this would be the thermodynamic reaction quotient. At equilibrium, delta G equals 0 by definition. So we set the expression here equal to 0. We can rearrange it. What happens to the reaction quotient? Well, if you make the equilibrium conditions, well then you would have to specify that this is the reaction quotient for equilibrium conditions. And that's what we call the equilibrium constant K. Okay, so when delta G equals 0, Q becomes K. And we have this relationship between the standard Gibbs energy of reaction and the equilibrium, the thermodynamic equilibrium constant K. You can combine this relationship here with this relationship, and it'll give you this expression here. And then we can do a quick little sign analysis. We see that if Q is larger than K, so if this fraction is greater than 1, natural log will be positive, and so the delta G will be positive in that case. That's this second criterion right here. That tells us that when Q is larger than K, the reaction is spontaneous in the reverse direction. If, on the other hand, Q is smaller than K, So we have a fraction here. Natural log of a fraction is negative. In that case, delta G is going to be less than 0, which is when the forward direction is spontaneous. And then for the third case, the equilibrium conditions, if Q equals K, natural log of 1 gives you 0, delta G is 0 at equilibrium. I often write these rules down here, these 3 rules at the bottom. I often write it in this way to help students remember them. I like to put the equilibrium constant in the middle, and then when comparing the equilibrium constant to Q, there's 2 possibilities. Either Q is less than K, in which case you write it on the left, or Q might be larger than K, and you can write it on the right. Either way, you need to get back to equilibrium. When Q is less than K, the arrow tells you to go to the right, so in the forward direction for the reaction. If Q is larger than K, the arrow points back towards the reactants, so you want to go back towards the reactant side. So this is a visual trick to help you remember these rules. This diagram, you may or may not find it a little bit easier to remember than the 3 rules by themselves. This is an interesting graphic here. It attempts to explain why. Why do reactions not go to completion? Why do some reactions stop before reaching the products, even when the standard Gibbs energy of reaction is negative? And so a couple of things are being illustrated here. First, the delta G standard, okay, is the difference in Gibbs energy between the products and the reactants. Okay, so the vertical drop that we see here in this graphic, that is delta G naught, right? In fact, this quantity here, assuming that value there is 1, that you go from 0 all the way to 1. So this is taken to be, what the Gibbs energy would look like, what the Gibbs energy curve would look like if you didn't think about the following fact, that as the reactants are forming, they are also mixing with the products that are being formed. So as the products form, they mix with the reactants, at the beginning part of the reaction. And if you went all the way to the end of the reaction, what would happen? It's as if you have mostly products that are then unmixing with the reactants. So as you go from all reactants to the middle of the graph here, it's like the products that are being formed are mixing with the reactants. As you go all the way to the end of the graph, it's as if you're unmixing the products and reactants. Okay? And as we've learned about previously, whenever you mix things together, that gives you an increase in the entropy of your system. So when you mix the reactants and products, that is, as the products form and they're mixing together, that increases the entropy of the system. But if you go too far, that would in essence be unmixing them, and that would decrease the system's the system's entropy. And as we know, spontaneous processes tend to increase the entropy of the system. So what's being plotted right here is just a very simple model of what it's like to mix things together. So you'll notice that the curve bottoms out right at the halfway point. Okay, so in going this direction, the Gibbs energy of mixing gets smaller and smaller and smaller, and then as you start to go towards pure products, it gets larger and larger and larger. So what we do is we take the unmixing, or we take the Gibbs energy of a reaction where you don't consider mixing, and add it to the Gibbs energy of mixing. And that gives you the true Gibbs energy curve for this particular reaction. And you'll note that the contribution of the mixing term serves to create a minimum that is between the reactants and products. And so if we go back to our rule that the Gibbs energy tends to a minimum when it reaches equilibrium, that means that the equilibrium point will not lie at the edge of the graph here. It's going to lie right here. And so that's the rationalization for why chemical reactions don't always go to equilibrium. It's due to this entropy contribution associated with mixing. And where that point lies depends upon the nature of the reactants and products themselves. It also depends upon the value of delta G naught in addition to what they're made of. So this curve also depends upon what you're talking about. What types of chemicals are reacting together. Well, the next set of problems here, they just go through different aspects of this. So in this relatively simple problem, they give us, we're considering an isomerization reaction from pentane to 2-methylbutane. We're told that the standard Gibbs energy of reaction is negative 6.7 kilojoules per mole. Calculate the thermodynamic equilibrium constant. You use this relationship here. That delta G standard is equal to minus RT natural log of K. They want us to find K, so we would write this as negative delta G naught over RT. This is a fairly standard general chemistry problem. So you're given delta G, R, you would use 8.314 times 10 to the minus 3 kilojoules per mole Kelvin. Temperature, you'd use 298 Kelvin. It's pretty easy to calculate. So I'm just going to leave that as an example problem for you guys to work. Here, this one is also fairly straightforward. In fact, I've already kind of worked one that was like this. For part 1 here, Q is going to be the activity of species C to the first power, the activity of species D to the second power, divided by activity of A to the second power, activity of B to the third power. Then they want us to calculate the equilibrium constant for this heterogeneous reaction, part 2. So for a specific reaction, so K would be, the equilibrium activity for the calcium oxide times the equilibrium activity for the CO2 divided by the equilibrium activity for the calcium carbonate. And what is written on the next slide are the conventions that we use for activities. For solids and liquids, the activity is taken to be 1. And so for both the calcium oxide solid and the calcium carbonate solid, the activities are 1, and so this just reduces to the activity of the carbon dioxide, which is not 1. Okay, so that you would measure. Very frequently, you would write it using the ideal gas model. You would write it as the pressure of the CO2 divided by the standard pressure. And so I'm going to write that as an approximation. And that's also discussed on the next slide. So there are many different ways to express equilibrium constants depending on what concentration unit you want to use. A very general way is to express the activity in terms of mole fraction, in which case the activity coefficients you're going to be working with are activity coefficients based upon mole fractions. And so here in this notation, we're giving it a little subscript x to denote that that's what that activity coefficient is based upon. Alternatively, you could use molarity or molality as your concentration unit, in which case you would define the activity as being a molarity-based activity coefficient times the molarity of the solution divided by the standard molarity, which is 1 mole per liter. For a molality-based definition, you would have a different activity coefficient, one that's based upon molality, times the molality of your solution divided by the standard molality, which is, again, 1 mole per kilogram. Now, as the solution that you're talking about, the reaction mixture, becomes more and more ideal, the activity coefficients go to 1, in which case you can simplify this expression and just simply write the activities as the ratio of the molarity divided by the standard molarity, or the molality divided by the standard molality. You can do the same thing with pressures. For a gas, if you want to take into account real gases, you would write the activity of the gas as the so-called fugacity of the gas, which has units of pressure. The way to think about it is an effective pressure, just like the way to think about activity as an effective concentration weighted by a little fudge factor here. You can think of the activity of a gas it's called the fugacity, and then the fugacity is an effective pressure multiplied by an activity coefficient. Now, when the gas is behaving ideally, that activity coefficient goes to 1, and then you can use this approximation here, which is what I used in the previous example, and that's what we've taught you how to do in your lower level chemistry classes. The bottom rule here is the definition of the activity for a pure liquid or pure solid. And so since it's defined to be unity, we do not include pure solids and pure liquids in our equilibrium constant expressions. And that is a rule that you would remember possibly from general chemistry. So you can define activity in terms of any concentration that you really like to. You just need to be upfront about it so you know how to define your activity coefficients when you do your measurements. And then as a consequence of that, you can express the thermodynamic equilibrium constant in terms of all sorts of different equilibrium constants. So here's the formal thermodynamic definition of the equilibrium constant, and here we're substituting in the definition of activity in terms of mole fraction. That product then separates into two products, one involving the activity coefficients and another involving the mole fractions. And so you can define this to be Kx, and this is the equilibrium constant involving the activity coefficients. And so this guy, you can measure that by, you know what the mole fractions are of the solution that you've prepared, or whatever reaction mixture that you have. So you know that by what you've done. You can calculate this guy by looking up the activity coefficients for each of your species under this set of conditions of concentration, and that allows you to calculate the thermodynamic equilibrium constant. The same approach works for molalities, it works for molarities, and it also works for pressures. Now, it's of course a lot of work to look up all these numbers all the time for every particular set of concentration, so I'm not saying it's an easy thing to do to calculate the equilibrium constant in this way. But it's understandable how to do it. It's also understandable that we typically like to simplify these calculations by simply taking these equilibrium constants involving the activity coefficients, just take them to be 1. So we typically ignore those terms, at least in general chemistry and in perhaps quite a bit of quantitative analysis as well. But if you want to be very, very precise, you would need to include these activity coefficients and the thermodynamic constants that are built upon the activity coefficients. Given these relationships here, you can establish relationships between each of these. I believe they're called apparent equilibrium constants. So you can derive a relationship between Kp and Kc. And I think, in one of the forthcoming problems, they want you to use, like, what is the relationship between K and Kx, I think, something like that. In any case, these are just constants. This is 1 molar, this is 1 bar. You've got the gas constant here, the temperature, so this is just going to be a constant for a fixed temperature. This delta nu, this is the change in the number of moles within your reaction. So let's see, what does this problem want us to do? Calculate the equilibrium constant for the synthesis reaction, for the synthesis of ammonia, and then show how K is related to the partial pressure of the species involved. So I'm going to start with the synthesis of ammonia. So we'll take nitrogen, we'll get some hydrogen in there, and we're going to make some ammonia. We'll just assume it's all gas here. And I'm going to go ahead and put a 2 there, and then a 3 there. So this will be our reaction for the synthesis of ammonia. Calculate the equilibrium constant. What you would need to do, you would use your thermodynamic tables to calculate delta G for the reaction. It will be 3 times the enthalpy of formation for ammonia, and then you would subtract, not enthalpy, Gibbs energy, the Gibbs energy of formation. And then, you're subtracting off 0 for the nitrogen and minus 3 times 0 for the hydrogen, because the formation Gibbs energies for these are 0. So you get that number. And then to get the equilibrium constant, what you would do is you would use this relationship Again, I'll leave that calculation. I'll leave all of these calculations to you. They're given in the textbook, but this is the idea. You would use the thermodynamics that we've already learned, the thermochemistry that we've already learned to calculate the delta G for the reaction, and then to get the equilibrium constant, you would use this relationship to find that. In the second part of the problem, show how K is related to the partial pressures of the species when the overall pressure is low enough for the gases to be treated as perfect gases. So here what I'm going to do is I'm going to set up an ice table, and let's start with, how do we want to start? We'll start with, I don't want to work the wrong problem here. Oh, never mind. We'll save the ice table for the next problem. I'm jumping the gun here. It'll be the activity of ammonia squared over the activity of nitrogen, the activity of hydrogen cubed. If the ideal gas limit holds, we can write this as pressure of ammonia divided by P0 squared, pressure of N2 divided by P0, pressure of H2 divided by P0 cubed. And so that gives us this, well, we could just leave it like that, really. That's what they were basically asking us for. So the equilibrium constant is related to the partial pressures. And again, this is an approximation when the activity of each species can be related as this ratio. So here's the problem where we need the ice table. So we're looking at the decomposition of water vapor is our reaction. So that would be H2 gas plus O2 gas. And I'm going to put a 2 there, a 2 there, and then we'll have just 1 mole there. So this is the balanced reaction. They give us the standard Gibbs energy of reaction. And so they want to know what is the degree of dissociation when the reaction is allowed to come to equilibrium at a total pressure of 1 bar. So the point of telling us the standard Gibbs energy of reaction, again, is so that we can calculate the equilibrium constant. So K will be equal to 10 to the minus the standard Gibbs energy of the reaction, which is given, divided by RT. That is going to be some number based upon this value and that temperature. So we know how to do that part already. Let's look at the ice table for this reaction, and we'll talk about the extent of dissociation, which they've defined in this problem. So we're going to imagine that we start off with some number of moles of water vapor. And I guess I've got I'm going to follow the stoichiometry that they did in the book. So they only put 1 here and here, and then they put 1/2 here. And then that's a little confusing. That didn't help. Anyway, we'll just start over. We'll do H2O, gas, to H2 gas plus, we'll follow Atkins' approach. We'll do 1/2 mole of gas. All right, so setting up the ice table, we've got a certain number of moles of water vapor and no products initially. Now, some amount of this is going to react based upon the definition that we have here. If we rearrange this, so normally we would be putting minus our extent of reaction plus our extent of reaction plus 1/2 our extent of reaction there. Nothing wrong with doing that. They're just defining it in a different way, right? What they're saying is this quantity here would be equal to N minus NEQ. Okay, and so if we were to rearrange that, I'll probably be putting my equilibrium line a bit lower. If we were to rearrange that in terms of what they've given us, this minus our extent of reaction variable is going to be equal to minus alpha times N. Okay, so that's the quantity that we want to use. So this is going to be plus alpha times N, and this is going to be plus 1/2 alpha times N. I should make that minus. There we go. So this is the change in the amount of moles of this substance. And then to get the equilibrium amount, you just add these together. So we're going to have N minus alpha N plus alpha N, and then 1/2 alpha N. So that's the equilibrium number of moles of each species. Another column that we can make is the total. So really what we're interested in is the equilibrium number of moles of gas. And so we would add all of this together. So we see that this term is going to cancel that one. And so we'll be left with N plus 1/2 alpha N. This is the total number of moles of gas at equilibrium. Let's calculate the mole fractions. So we're going to be taking the moles that we have divided by the total number of moles that we have. And so that's going to give us, it looks like 1 minus alpha divided by 1 plus 1/2 alpha. This is going to be alpha divided by 1 plus 1/2 alpha. And this will be 1/2 alpha divided by 1 plus 1/2 alpha. Those are the mole fractions. And if we make the approximation here that the total pressure is, well, the total pressure is 1 bar, that would indicate for this reaction that the value of the extent of reaction is very small. Okay, so that means what we're saying here basically is that not very much of the water vapor is going to decompose at 1 bar pressure, and that makes sense. You know, these are strong covalent bonds that are holding the water together, so alpha is going to be fairly small. So we're going to take alpha tending to 0, and that allows us to then simplify this line of this extended ice table. So in that case, we can neglect alpha relative to 1, and so this is going to give us minus, you know, we might wait on that until let's make this approximation a little bit later just to make it better. So let's go ahead and next assemble the partial pressures. So this will be the pressure line. The partial pressure of the water vapor will be the mole fraction of water times the total pressure of 1 bar. So I'm just going to call that standard. And here it's the same thing, alpha P standard over 1 plus 1/2 alpha, 1/2 alpha P standard over 1 plus 1/2 alpha. Then when we want to assemble the equilibrium constant, what we'll do is we'll take the partial pressure of water vapor divided by P0. Oh, not water vapor. We want to do the products first. So hydrogen divided by the partial pressure of O2 over P0 to the 1/2 power divided by the reactants. So that'll be PH2O divided by P0. And so this is the equilibrium constant expressed in terms of the partial pressures. We have the partial pressures here expressed in terms of the extent of dissociation, and so we just make the substitutions in there. So that's going to give us starting with the products here, so that's going to give us alpha over 1 plus 1/2 alpha, and then we'll have 1/2 alpha over 1 plus 1/2 alpha to the 1/2 power over 1 minus alpha to the 1 plus 1/2 alpha. We'll notice that all of the P0s cancel out. And then what I'm going to do next is then make this assumption that, okay, the extent of dissociation is going to be rather small. And so what we'll say is that we can neglect alpha relative to 1. We can neglect alpha relative to 1 here. We can neglect alpha relative to 1 here. And so it's going to simplify the expression considerably. And so we'll wind up with alpha 1/2 alpha to the 1/2 power divided by simply 1. Because we can neglect the alpha both in the numerator and the denominator here. And so we'll get 1/2 alpha to the 3/2. So we've expressed now the equilibrium constant K. Unfortunately, it doesn't all fit in one line. Here, I'll write it on another piece of paper. What we found is K equals 1/2 alpha to the 3/2. And as I said before, you can calculate K as 10 to the minus, it'll be the delta G for the reaction divided by RT. So you can calculate that quantity. You can then solve for alpha, which is what they wanted us to do. So here I've put together, using ice tables, an expression for this degree of dissociation, which you can then combine with the equilibrium constant to find that value of alpha. Here, this one's not nearly as interesting. Again, it's going back to these relationships here between the different equilibrium constants. Okay, and so what they want you to find the relationship between K and Kc. I'm just going to copy the equation from the book. It's really just a bunch of unit conversions, and so you wind up with this expression here. Let's see, I should have gone one step further, I guess. Kc times C0 RT over P0 to the delta nu. What they point out here is that the value of P over C0R is 12.03 Kelvin. So again, these are just constants, so everything's a constant there. Here you'd be plugging in the temperature, probably you'd plug in 298 Kelvin. And then delta nu for the ammonia synthesis reaction. So if you've got H2 and N2, let's do 1/2 and 3/2 equals NH3. Let's suppose that's the reaction we're working with. Here you would write delta nu would be 1 mole minus 3/2 moles minus 1/2 mole. So that's going to give you a minus 1. So you would plug in, for this ratio here, it would be T over 12.3 Kelvin to the minus 1 power. And so that would be the relationship between K and Kc. I'm going to go ahead and stop the video here, and we'll pick up with Le Chatelier's principle in the next one.